We learned how to convert decimal to hexadecimal, and yeah, for example, we learned to convert positive numbers and negative numbers to decimal or hexadecimal. So from decimal to hexadecimal, and we learned the types of data types. So we learned bytes. So what is a byte? It has 8 bits. And what is a word? It has 16 bits, or you can say 2 bytes, or I can write here. So byte is like this, and hexadecimal digit 1, 2, and a word is like this, 2 bytes, and hexadecimal digits will be like this, and double word is 32 bits, and that is 4 bytes, and each byte has 2 hexadecimal digits. And for reference, if we are making a byte like this, then each digit means 4 bits. That's how it makes up byte. 0, 0, 0, 0, 0, 0, 0. So we will usually use this as a byte. This is just for reference, but in the exam we will mostly have bytes or words or double words. So we learned these data types, and we learned decimal, hexadecimal, binary, and how we convert negative numbers and positive numbers from decimal to hexadecimal. Now, how where is this all of this data that we are talking about is stored? So data is stored, data storage. Let's see, data storage in computer. It's first of all we will talk about registers. Data is stored in registers. It's not stored, but registers are more of like a temporary storage, and it's used for doing calculations. So we won't call it storage, but yeah, it's a part of computer architecture, registers that we will talk about. And there is the actual data storage, that is the memory, which is more of like a permanent storage. But I mean, we can also delete from memory things from memory, but yeah, registers are faster to change their state, so they can do very fast calculations, and memory is very slow. That's why it's permanent, and that's why we don't use really memory to do calculations, because it is supposed to be permanent. And yeah, so we will learn about registers and memory. So for instance, here we learn, yeah, in registers, there are types of registers. We will learn about types of registers, but in registers, the data is stored as we talked about, like this, and um, first of all, of course, in bits, but we represent it in bytes, like this. So, for example, this is a double word, and in double word format, for instance, this is if if I can write here E, and this is -2. in decimal format. And in memory, this data is represented slightly different. So what happens in memory is that a high order, the digits that come first goes in first. So FF. Similarly, if I just copy this, not done, copied. Okay. So in double word, in memory, if we look at the storage, this is how it's stored. So finally, FE. So you can see the order is swapped. So FE comes first, then FF, then FF, then FF. There is a reason for it. The reason is that the calculations are easier with this in memory. Like it always saves it much more easier. And when we want to use like multiplication or division, then it's easier to just use the lower order digits. That's why it's stored in memory like this. But yeah, you just need to remember that in registers it's like this, the normal, and in memory it's swapped. So for example, um, these are the examples. Alpha is a byte. So what was a byte? Byte was, we just represent like this. And in the byte, we want to write 41 in hexadecimal format. We just write 41 hexadecimal. So hexadecimal alpha. This is alpha, whose value is 41 in hexadecimal format. Also, if you want to convert some value, for example, 41 from hexadecimal to decimal, we do the similar steps as we did in decimal. So from left to right, we write the powers. So it's in hexadecimal form. That's why powers will be of 16. And we multiply these digits as coefficients. So 4 times 16, that is 64, plus 1 times 16 power 0, which is 1. So 64 plus 1, which is 65. So what it means that 41H is basically 65 in decimal format. 41H is 65D. Yeah, so that's how, this is how it works. And another example you can see here is beta, and it's a word. This means basically that each of this number will be stored in word. So first of all, let's try to write it in normal order. So one in hexadecimal in a word. In word, there are 2 bytes. So this is 2 bytes. We write 01, 00. And secondly, if we want to write 257, and in hexadecimal, we need to convert this 257. So 257 divided by 16, that will be 1. 16 minus 97, and that is 16. 96 minus 1. So here you can see that it is 16. Whenever it is 16, there will be a difference. Whenever this number will be greater than 16, For example, we want to convert 257 decimal to hexadecimal. So we represent it like 16 power 1. There will be 16 power 0. There will be 16 power 2. Or maybe let's just say there is 16 power cube as well. So usually what we do is we estimate what highest power can this go. So 257 is basically closest to 16 square. So that's why we usually divide it with 16 square, which is 256 power 256 times 1, 56, 1. So what is this? So it's 0 times 16 cube plus 1 times 16 square plus 0 times 16 plus 1 times, this is the remainder. So we just basically need to divide this number in terms of powers of 16. So 16 square and 16 power 1 and 16 power 0. So if we try to represent this, this will be 0, 1, 0, 1. And this is 257, 257D in terms of hexadecimal. 0101H. So if we want to write this in word, we just write 0101. So this is 257, and then this was 1 first of all, then 257, and then minus 2. And how do we represent negative numbers? Negative numbers. First of all, minus 2D. First of all, we write the positive value of this, and what we are doing is we are trying to get a word, so we write it in word form, and 2 in hexadecimal is just basically 2. And then we subtract this with one extra digit, 0, 0, 0, 2. And in hexadecimal, instead of getting 10 here, we will get 16 because there are 16 possible values. Instead of getting 15 here, 16, 9 here, we get 15. Because we are not working with decimals, so that's why you have to change accordingly. So 16 minus 2 is 14, and 14 in terms of hexadecimal is, so 10 is A, 11 is B, 12 is C, 13 is D, 14 is E. So that's why we write E here, and 15 is F, so F, 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 F. And when we represent this, it will be F, 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 E. This is minus 2. Now, each of these particular values, this is the normal conversion, but in terms of memory, it will be swapped. So in memory, these numbers will be like this. So each byte will be swapped. So 1, 0, not 1, 0. It's 0, 1 here. So 0, 1 and 0, 0. And then we will swap this as well. 0, 1 and 0, 1. Then we will swap this as well. So FE and F, F. This is how these numbers are represented in memory. 0, 1, 0, 0, 0, 1. Did we mess up here? 256. 01101 is it? 16 square. Just a second. So if we try to write this in normal form, it will be 1001 because it's swapped. So in the normal form, it will be like this. And if we want to try to convert this into decimal, you can see that 1 times 16 power 0 is 1 plus 0 plus 0 plus 16 cube. So this is represented as wrong here. 257 should not be like this in memory. 257 should be like this in memory. And finally, minus 2 is correct. Yep, FV and FF. And this as well, message. So byte, each character is in a byte, and the final byte is 00. And character double word. So these are also represented character by character. So only only when we try to assign, for example, there are 2 bytes, and we want to send these 2 bytes all together into memory. Only then it will swap. For example, 0110. If you want to save this into memory, it will be swapped to 10 and 01. So that's basically about memory. Now let's go on to registers. Yeah, so now let's look at the registers. So there are, first of all, types of registers. EAX. EAX is the most used. There is no particular use for it, but yeah, it's usually used for results, and it's, as it says, it's accumulator. So usually when I will explain when there are no other operands available. For example, in case of division, it always divides EAX because it's the accumulator, the data accumulator. It accumulates data. And then there is EBX. There is no specific use for it. You can use it anywhere. And ECX can also be used anywhere, but usually we use it for as a counter for loops. EDX is basically it stores data in terms of when we do division or multiplication. And then there is ESI, as the name suggests, it's source index. It's used to point the index. In EDI, it doesn't have specific use. And then there is ESSP, which is the stack pointer. This will be very useful as well. It points to the top of the stack. Then there is EBP. There is no specific use for this in this course. Base pointer, but no need. So these are the types of registers, and each register is of 32 bits. Full register is of 32 bits, and each register can be looked at as smaller parts. So, for example, you can see that EAX. So EAX. So this, if this is full EAX, then this is AX. Let's move it here. And AX also is divided into smaller parts. So this is AL and this is AH. So if this is 32 bits and every 8 bits form a byte, so there will be total 4 bytes in AX, and this is how we will represent it in form of bytes. AX will be 2 bytes and AH and AL. This is AH is 1 byte each. And other registers also have these kinds of divisions. So now this is the question that might come in exam. Just a second, I will create a new page. So what does it say here? Copy integer value 42 to register EAX. So 42 integer value, so 42D into EAX. And EAX has 4 bytes. So 1, 2, 3, and 4 bytes. And copy. These instructions we will learn soon. But if we just want to represent 42 in this form, it will be 42 to, first of all, let's convert it to hexadecimal. So divide by 16 goes twice, 32. 10 is the remainder. So if we want to represent it, it will be 16 power 1. So 2 times 16 power 1 plus 10 times 16 power 0. So it will be 2 from here and 10 from here. And 10 in hexadecimal is A. So 2A, 0, 0, 0, 0, and 0, 0. So EAX is represented like this in 42D is represented like this in register EAX. But if we want to copy the value of register EAX to memory, double word X. So that means we want to copy this value to memory in form of double word. And double word was, if you remember, 4 bytes. So the same as here. So if we copy 4 bytes and this bytes into memory, what will happen is that it will get swapped to a 0, 0, 0, 0, 0, 0. So this is 42D in memory. And each, so double word X. So there is a variable X. So this first position will be known as X. This position will be known as X plus 1. This position will be X plus 2. And this will be X plus 3. Just like here. So 2A, 0, 0, 0, 0, 0, 0. So it got swapped. So that's how memory and registers work. This should be enough for the first type of question that there might be. So for example, let's try to mm, Or actually, first let's implement. Let's try to understand this. So A is a word whose value is 2 in memory. So memory field A whose value is 2, and it's a word. That means it will be 2 bytes. And in memory it will be swapped. Instead of being 0002, it will be 0200. And this will be address A. This will be A plus 1. And if we copy this into a register AX, just AX, then it will be 00 and 02. Or if we copy this into EAX, it will be, we don't know what's in the first place because this was word format. It just had 2 bytes. We don't know what is in the rest of the 2 bytes in EAX. And here it will be 00 and 02. Yep. Maybe we can try to solve some question at least. Ask one. Yeah, let's try to solve this. So task is integer numeric value n word format is defined. So n word is 266. Write internal hexadecimal code. So this is in memory as it has a variable. If there wasn't a, whenever we define something, it's always saved in memory. So 266, it's in hexadecimal, starting from the address n. So a word has 2 bytes. So we draw 2 bytes. And we also convert this into hexadecimal. 266 divided by 16, 106, which will be 96. So once goes once and then it goes 6. So whenever we get 16 here, you have to do it again with 16 square, 16 square, which is 256, 10. So now if we represent this, it will be 1 times 16 square plus 0 times 16 plus 10 times 16 power 0. So from here we can get the value. It's 1, 0, and 10 will be A. And if it's word format, so A, 0, 1 here, and 0 will be. So this is in normal form, but we are doing in memory form. That's why it will be swapped. 0 A and 0, 1. So that's the answer, 0 A, 0, 1. And the address is N and N plus 1. This question will be definitely in exam. So as its example, just the values will be changed. So another example can be M double word and -5. So let's try to represent this first of all in hexadecimal. And double word, so there are 4 bytes. So normal will be like this, and the memory will be swapped. So we will write it here. So -5 into hexadecimal. Let's try to convert it. So first of all, we write 5 positive 5 in hexadecimal in double word. So 00000005. And we subtract this from one extra digit. And when we subtract, again, 15, 15, 15, 15, 15, 15, 15, and here 0. 16 minus 5 is 11. And 11 in hexadecimal is B. And all of these are F, 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 and F. So here if we represent this, it will be F, F, again, 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 and FB. And in memory, it will be the opposite. So FB byte comes first, then FF byte, and FF byte, and again the FF byte. And if we write the address, so this is address M, this is M plus 1, this is M plus 2, this is M plus 3. Yep, this is one of the examples of how the questions will be. And in the next video, we will learn the common simple instructions. So add, subtract. So we will be able to do not this one, but yeah, some of these we will be able to try and solve. Yeah, this is a common, a simple instruction, and this is a simple instruction. Yep. In the next video, we will learn simple instructions.